Welcome to our video notes for section 6.1. This section is the very beginning of chapter 6. We're going to talk about something called slope fields and Euler's method, but first we're going to start talking about what's called differential equations. You guys have met differential equations throughout the textbook. They are equations that essentially have an equal sign, but also involve a derivative. So we've seen these before where we've just been verifying that something is a solution. There's lots and lots of examples you could make up. For example, y double prime minus y equals 0. This would be saying, tell me a function whose second derivative minus the first derivative is equal to 0. Or for example, y prime equals x minus y. What kind of derivative would be such that, or what kind of function would be such that its derivative was the difference between x's and y's? Again, a differential equation is any equation, so it has an equal sign, that also involves derivatives. And unlike your algebra courses where the solution to an equation was a point, here the solution to our equations are going to be equations themselves. So just like we said, a solution is one that satisfies the given equation. All throughout, probably even since chapter 2, they've had you do things like example 1a, where you're verifying that a function is indeed a solution. So if I tell you that my differential equation is xy prime minus 3y equal to 0, then in order to verify that y equals cx cubed, I would need to plug it in. Well, the it here, though, is going to involve also computing the derivative. So we're assuming that that c is a constant, so this would be 3 times cx squared. And I would go back to my original formula, be xy prime minus 3y equal to 0, and I would see if things worked, right? X is just an x. Y prime would be 3cx squared minus 3, and instead of calling it y, let's call it according to x's. So cx cubed, and we are essentially saying, is this truly equal to 0? Well, do the multiplication, right? X times x squared, that would be 3cx cubed minus 3cx cubed. We have a true statement. That means that y equals cx cubed is a solution, or we could say that it satisfies the differential equation xy prime to xy prime minus 3y equal to 0. So verifying is as simple as plugging the function in. You might have to do a little bit of extra work to fill in any derivatives. Find the particular solution. Just like when we did integrals, here they're saying, okay, so now if that is my equation, y equals cx cubed, then which c value would go through the point negative 3, 2? So y equals cx cubed, knowing that that is a solution, and that when you plug in a negative 3, you get a 2, we could determine that c is a negative 2 over 27. So the particular solution would be negative 2 over 27 x cubed. That function would satisfy this differential equation, and that function would also pass through this coordinate. So that's sort of the best case scenario. When you know that something is supposed to be, verify kind of implies that it's going to work. A more difficult question sometimes is how do you find this? How do I look at this equation, the differential equation, and determine what even to test? And that is the rest of the chapter. So there are really two ways to talk about solving differential equations. And those methods are analytical methods. So really analytically in math means that you're going to do some sort of computation, algebra, or calculus. We're going to be able to use symbols and come up with our solutions. Another is a graphical solution. And we'll get to that. We'll talk about slope fields towards the end of this note set. You guys have been doing a little bit of really basic differential equations already. We showed them to you in 4.1, and we've been working through them a little bit here and there through chapters 4 and 5. We talk about something when we want to solve analytically, we talk about separation of variables. I want to get all my y's on one side, all my x's on the other. And in 6.1, they focus on fairly simple separations where all you need to do is multiply the dx to the other side. So for example, to write this one with x's solely on the right-hand side, I would need to multiply both sides by dx, rewriting my equation in that differential form. I would have e to the x over 1 plus e to the x dx. In that case, I have separated my variables. And then I would go ahead and it would be like saying, well, tell me what function has this as its derivative. How do I do that? I integrate. The integral of dy, there's a 1 here, so I would get a y. And we've talked about this before, but the convention is to put a plus c only on one side. Over here, I would have to get a little creative, right? I would need a very nice u substitution. If the denominator, 1 plus e to the x, is my u, then the derivative would be e to the x dx, which I have in my setup. So e to the x dx is going to become du, and over u. This is u to the minus 1. This is my logarithm. So y equals the natural log of the absolute value of u plus c. And I would want to back substitute. That would give me y equals the natural log of the absolute value of 1 plus e to the x plus c. In this case, I could have also dropped the absolute values because that function would always be positive, but it's not terrible to have them there either. So that is a nice, easy analytic version. And all of the ones in 6.1 are going to be that simple, where you just need to move the dx over, and then you can practice integrating just like we have been for the last 2 chapters. The deal with chapter 6 is that we will revisit analytical methods in 6.2 and in 6.3. In each section, they'll make it a little bit more work to separate out your variables. But for now, they're all pretty straightforward. Graphical methods, we want to talk about something called a slope field. So with a slope field, what we're going to do is we're going to look at sort of the image and try to imagine what that would mean for the function that would satisfy the particular derivative that's being given. So a couple tricks. When you are setting up a slope field, we want to create an XY plane. And we're going to zoom in pretty far. You do not want to make your graphs very large when you're graphing a slope field. So I'm going to just plot 2 in each direction. And so here's what's really happening. I wish I would normally write on my board probably at this point, but let me grab a sticky note and just cover this for a second. Imagine that you had a function, and way back when we first started talking about derivatives, we talked about the slope of the tangent line at a given point. And we would maybe make these little markings to say and talk about the slopes of our tangent lines, right? So it's a very negative number, right? It would be going towards negative infinity. Here it's getting closer and closer to 0 until you're at the bottom. And we used these little markings to get an idea of what the derivatives would look like relative to the curve. A slope field is the reverse of this. So imagine that I took just those little markings and I said, hey, what curve would give me marks that look like this? That is what a slope field is. You're working backwards. You're looking at the markings, those tiny little slope marks, and you're trying to sort of envision, well, what kind of curve would make these as its slope field, as like a picture of all the slopes of that curve. So hopefully that makes a little bit of sense. But we're essentially kind of working backwards. We're starting with the derivatives and trying to sketch back in the curve. And your job with a slope field is to generate those tiny little markings. So they're going to have to tell you how to do that. So here we've been given dy dx is equal to x. So the slope of my curve is exactly equal to the x coordinate. What you can do is you can plug in your points. So for example, I have quite a few points here, right? 1, 2, 3, 4, 5, and I've got about 4 lines. So I've already got about 20 coordinates, and that's why we don't want to go very far to the right or to the left. And I'm going to just pick a point, and then I would evaluate the derivative at that point. So at 0, 0, if the slope is equal to x, then for that particular point, the slope would be equal to 0. And what I do is at that mark, I make a tiny little slope line and indicate that it would be horizontal because the slope is 0. And I would do this for all my points. I would think to myself, dy dx at the coordinate 1, 1. Well, if the slope of the curve is equal to x, then at 1, 1, the slope is 1. And I would think about what a slope of 1 would look like, right? That would be almost like a 45-degree angle. It's a nice, easy slope. And the trick is that you don't want to do this at every single point, right? You want to be able to make some sort of generalization. So every time that x is 0, I would get a slope of 0. Well, x is 0 along the y-axis. So I could make those little horizontal hatch marks all along the horizontal. And every time x is 1, I would have a slope of 1. It doesn't matter if I'm at 1, 2, or 1, 0, or 1, negative 1, right? The slope is dependent at 1, or on x. And so when x is 1, I would have the same slope. What's going to happen when x is 2? All up and down that vertical line, I would get a slightly steeper slope, right? A slope of 2 is slightly steeper than a slope of 1. That's another reason we don't want to go out too far. A slope of 3 would be steeper. It's just a little bit hard to draw once you get above about a 1 or a 2. On the other side, though, right, I would have a slope of negative 1. So for example, at the coordinate negative 1, 0, my slope would be negative 1. So it would be that nice sort of relaxed angle, and it would be going downhill. And that would be true at all of these values. And so I would sketch them in. When x is negative 2, right, I would have sort of the same steepness, but I would be going downhill. So I would try to sketch in a slope of negative 2. And then once you have them all here, it's a little hard to see, but the idea being that you could sort of sketch in a curve and see that there was sort of a parabolic shape to these images. That one was relatively easy. It only depends on the one variable. Let's try another. We can try this one. So here I have a different slope, right? My slope would be determined by negative x over y. The process is the same. I'm going to graph just a few units in each direction. And I would want to think about plugging in those values, right? So for example, every time that x is 0, I would be plugging in 0 over a number, right? I do have to be a little bit careful. Can I plug in 0, 0? Is 0, 0 going to have a derivative here? Well, the answer would be no. You'd get the indeterminate form. In that case, I want to leave it undefined. I'm going to leave it completely blank at the origin. But if you were at 0, 1, you would have 0 divided by 1. That would be 0, and you would indicate a slope of 0. Right? 0, 2, you'd have 0 divided by 2, negative 1 divided by 0 divided by 2, 0 divided by negative 1, and 0 divided by negative 2. So up and down the y-axis, those are all locations where x is 0, and I would just get a slope of 0 at those spots, right? I could pick some more points, right? At 1, 0, now here's an interesting one. If I am using the coordinate 1, 0, then my slope would be negative 1 over 0, and I would have an undefined. Now this one is a little bit tricky. Some textbooks will graph nothing because technically the slope does not exist, and others will graph a vertical line. So we're going to use the vertical lines here to represent that I would have a vertical tangent. 0 over 0 is indeterminate form. Dividing by 0 would represent that infinite slope on my graph. So that would be true, though, at any coordinate where I was dividing by 0. So I would have little vertical lines at each of those markings. And that just leaves me with a little square to fill in on each of these. So imagine that you're sitting at 1, 1. That would mean that you're plugging in 1 divided by 1. It's negative, so I would draw in a slope of negative 1. Right? If I'm at 1, 2, then I'm going to get a half. It's negative, so what happens when your slope is a fraction between 0 and 1? It would be slightly flatter, right? It wouldn't be quite 0, it wouldn't be as steep as a negative 1, but I want to be going downhill, and it would be about a slope of a half. At 2, right, at 2, 1, I would be getting a negative 2, so this one would be getting steeper. And then here I would be getting -1. 2 divided by 2 is 1, and it's a negative. So I would have that nice diagonal. In fact, if I think about it, as long as x and y are the same coordinates, I would have that slope of 1. So for example, -1 over -1 would be 1, put a negative in front, and I'm going to have like a diagonal here going where the values would be the same, giving me a slope of -1. If I was at 1, -1, this would plot as a positive, so would 2, 2, and this one here, and this one here. And then you can just go back and test the rest of the values, right? This would be the negative of -1. That would be a positive 1/2, so a little bit flatter. This one is going to give you, what, 2 over a 1, so that would be 2, a little bit steeper. And you can start to sort of see the patterns. And let's see, that one will be negative. Over here I'm positive, I'm a little flatter, and I'm a little steeper. You can connect these back to the analytical methods. You could look at dy dx and say that dy is equal to x dx, and therefore y is x squared plus c, and that would help you see sort of the parabola in the shapes. Any idea what's happening over here? Right? What does it look like? They look kind of circular, and we could do that. If we separated the variables, that would mean that we'd have to multiply y times dy to collect the y's on the left, and I'll keep my negative, so x dx, to multiply and get x's on the right. If I integrated both sides, I would get y squared over 2, and I would get negative x squared over 2 plus c. So what's happening here, if I double everything, right, I'll have y squared equal to negative x squared plus c. If I imagine adding the x squared to the other side, I can indeed show that analytically, I would also be getting that circular shape. The other thing that they will sometimes do with slope fields is to create multiple choice or matching. So on the next page, I have a nice matching one. This is great for the multiple choice questions. They wouldn't do a matching per se, but they might give you a slope and ask you which of the following could be the slope field, or they might give you the slope field and ask you which one matches up. The trick is that you don't want to sit here and graph all of these. You want to think about those patterns. So for example, we just graphed this one, right? What would I look for in number 10? I would be looking to think, well, every time x is 0, I should have a slope of 0. So I should see those values going right up and down the y-axis, because that is where x would always be equal to 0. And I can see that pattern, you know, when x was 1, I had all the same value. When x is 2, I have all the same value. That's true over here, but it doesn't correspond. So see how I'm at a positive x, but I also have downhill slopes. So this would be letter B. Right? Another one that I could think of would be, again, with zeros. What would happen? What would help me identify this would be that when x is equal to y, I would expect dy dx to give me a 0. And what would that look like? Well, that would look like that diagonal. So I can see on that diagonal all the 0 slopes are informing me that 8 should be letter D. Right? What would cause a 0 here? That would have to happen when y was equal to 2. And notice on letter A that about 2 units up, I have this nice horizontal line. So every time y is 2, I'm getting a 0 for my slope. And then I suppose at this point, we've got process of elimination, but you can also see that sine wave. You could pick out a specific value. When x is 0, I can see those zeros, and so on. 7 is letter C. So we're going to practice a little bit today in the homework, and then also tomorrow we're going to do some more work with slope fields. They're asked about fairly commonly on your AP tests. Sometimes you have to draw them, sometimes you have to do some matching. That's it for day 1 of notes. We're going to pick up with the last page in day 2, so check out the next video.